welcome to the University of Adelaide's Electrical and Electronic Engineering 1A Impact Tutorial for Module 4, Part 4. In this session we're going to be going through just a quick discussion upon propagation delay of ICs. The IC that we'll discuss in this instance is a trusty old D-type flip-flop that we covered in the last section. I'm not really interested in its particular configuration at this stage, just looking at how it just operates. I'm not interested in any external circuitry. Here I've drawn up a timing diagram. Timing diagram is what we discussed in last session. In this instance, we're going to be using a clock pulse at 100 megahertz. So it's the clock period. This instance will be 100 nanoseconds. Here you can see my lines in blue indicating each respective time slice. So this instance, this first item at the top here, this is our clock pulses that we've got. And we've got our data pin. This is just some data that's been putting into the system. Here we have Q, which is the output of the system, this particular device, and just operating with a propagation delay of 0 nanoseconds. These last three here that I've drawn down the bottom, we're looking at Q with a time of propagation delay from low to high of 25 nanoseconds. This is an item that you should be able to pull off the data sheet for each respective integrated circuit you're working with. So looking at a propagation delay, you might be TPHL for period of propagation from high to low. You might have slightly different labels for whatever data sheet you're looking for other ICs. This is I've drawn one with a propagation delay of 25 nanoseconds, this one for 80 nanoseconds, this bottom one here with 110. This propagation delay starts to become of interest when the propagation delay becomes greater than the period of the clock. That's why I've drawn three here. What we want from the behaviour of each latch device, or each particular IC, is to make sure its output is correct by the next time slice. Okay. So at this point here, for this individual Q, we should have high output just before here, which we do, that's correct. Over here, this instance should be high before, which it is, it's good. Should be low over here, which it is. Should be high here, which it is. And it should be low there, which it is. So 100% accuracy. Beautiful. So that's our ideal model. Now if we discuss this thing with a 25 nanosecond, once again, high here, that's correct. It's correct there again. Correct there, correct there, correct there. 100% accurate. Even though it takes 25 nanoseconds for this input, input to propagate to the output pin. It's all good and well. Once again, for the 80 nanosecond here, we're correct. Correct here, correct here, correct, correct. So 100%. Alright. This is the interesting case. For this case, 110 nanoseconds, quite obviously, it's going to be greater than the clock period. So, this instance, we're looking for a high, no, she's low. At this point, it's high, we've got high output, correct. At this instance, we want a low output, no, it's not low, it's high. It's incorrect there, and there as well. So it's only accurate about 16% of the time. 1/6 for this particular input data set. For other data sets, could be much better. So we can describe this system with a couple of simple rules. Firstly, if the propagation delay from low to high is greater than the clock period, the system is going to have errors. These errors are caused by the clock frequency being too high for the propagation delay, or the propagation delay being too high for the clock period. One and the same thing, just from a different perspective. This instance typically happens for PC overclocking. Now PC overclocking is a really good instance that ties together some of the theory that we've learned in lectures, some stuff I've just gone through with propagation delays here in the practical, and some real world experience. What PC overclocking is about is trying to drive a CPU faster than its rated frequency. So trying to push a 2 GHz processor out to 2.2, 2.5, sometimes even as far as out to 3.3 GHz. However, as we just discussed, if I'm pushing it beyond its rated frequency, I'm going to run into these sorts of conditions here, where I'm going to start having errors. So to reduce errors, I need to decrease the propagation delay. This is usually done by increasing the VCC. If you have a look at the data sheet for the 4013 as an example, you notice that the propagation delay decreases as you wind up VCC. It's stepped there as 5 volts, 10 volts and 15 volts. And the propagation delay correspondingly drops. However, if we increase this VCC, the power consumption of the system will increase. Okay? And remember, inside these devices, inside each IC, there's a whole heap of resistors, a whole heap of other devices. So if we, just on basic terms, if VCC increases, the power through each resistor will increase. So remember, P is equal to V squared upon R. As a consequence, what's going to happen is the heat that's going to be produced in the system will increase. Now remember, if you look back to the first video that I shot on the Module 2 primer, when we set fire to the resistor, it had too much power trying to be consumed through it. It got really, really hot. Magic smoke escaped. This is exactly what's going to happen with any IC or any processor, any CPU. Remembering, a CPU is just a fancy integrated circuit. Therefore, if we want to try and keep it cool, we've got a couple of options to us. Where you can stick a couple of big heat sinks on it, stick your fan on it, and try to push the air away. That's what's done in most CPUs, and even on some GPUs, that's graphical processing units, on some really high-end fancy video cards. Or we can take it another step and go through to water cooling. Water cooling, bit of an art form, quite interesting adaptation and how an extrapolation extension well beyond what we teach in this course. And in fact, it's really a bit of a DIY. I wouldn't advise you to do it at home, but for interest's sake, it ties together nicely. Some of the stuff we teach in the lab with real-world experience. If you want to see what water cooling processes look like, go search YouTube for water cooling CPUs. There's literally thousands of videos of guys that have done this. Why you would? Don't know. Because you run a high risk of squirting water cooling water all over the inside of your case, frying your video card, frying your RAM, frying everything basically if you swing a leak in the pipe. Not so cool. But there you go. Thank you.